Nice to see you again. In this video, we continue to review 20 questions from 211 to 230 in the series of 250 questions of the Google Cloud Professional Cloud Architect exam. Let's get started. Question 211. You are implementing Firestore for Mount Kirk Games. Mount Kirk Games wants to give a new game programmatic access to a legacy game's Firestore database. Access should be as restricted as possible. What should you do? Create a service account SA in the legacy game's Google Cloud project, add a second SA in the new game's IAM page, and then give the organization admin role to both SAs. B. Create a service account SA in the legacy game's Google Cloud project, give the SA the organization admin role, and then give it the Firebase admin role in both projects. C. Create a service account SA in the legacy game's Google Cloud project, add this SA in the new game's IAM page, and then give it the Firebase admin role in both projects. D. Create a service account SA in the legacy game's Google Cloud project, give it the Firebase admin role, and then migrate the new game to the legacy games project. Okay, this question from the Mount Kirk Games case study is about securely connecting two different applications running in separate Google Cloud projects. The main goal is to give the new game access to the old game's database, but to do so with the most restricted permissions possible, following the principle of least privilege. With that in mind, let's look at our options. Let's start by looking at the options that are immediately wrong because they are not secure. Options A and B both suggest granting the organization admin role. This is the most powerful permission in all of Google Cloud, and you should almost never grant it to a service account for an application. This is a major security violation and the exact opposite of as restricted as possible. Next, let's look at option D. It suggests migrating the new game into the legacy games project. This is also incorrect. This is a huge, disruptive architectural change and doesn't solve the problem of granting secure access between two separate projects, which is what the question asks for. This brings us to option C, which is the correct solution. This describes the standard pattern for secure cross-project access. You create a single service account to act as the identity for your application. You then grant that specific service account the permissions it needs in both the new project and the legacy project. By using a dedicated service account and a specific role like Firebase admin, you are granting only the necessary permissions for the application to do its job, without giving it excessive power like an organization admin. This is the best practice for a secure, least privilege architecture. Therefore, the correct thing to do is C. Create a service account in the legacy game's Google Cloud project, add this SA in the new game's IAM page, and then give it the Firebase admin role in both projects. Question 212. Mount Kirk Games wants to limit the physical location of resources to their operating Google Cloud regions. What should you do? A. Configure an organizational policy which constrains where resources can be deployed. B. Configure IAM conditions to limit what resources can be configured. C. Configure the quotas for resources in the regions not being used to 0. D. Configure a custom alert in cloud monitoring so you can disable resources as they are created in other regions. Okay, this question is about cloud governance. The goal is to enforce a rule across your company's Google Cloud environment that restricts where developers can create new resources, limiting them to only your approved operating regions. With that in mind, let's look at our options. Let's start with option D, which suggests creating an alert to find and disable resources after they are created. This is a reactive approach, not a preventative one. The best security practice is to prevent non-compliant resources from being created in the first place, rather than cleaning them up after the fact. Next, option C suggests setting quotas for all resources to 0 in the regions you don't want to use. While this might work in theory, it would be an enormous and unmanageable amount of manual work to configure this for every resource type in every disallowed region. Option B proposes using IAM conditions. While IAM conditions are useful for adding context to permissions, they are not the primary tool for enforcing location-based restrictions on resources. There is a more specific and appropriate service for that. This brings us to option A, which is the correct and Google-recommended solution. The Organization Policy Service is designed for exactly this purpose. It allows you to set broad constraints on your cloud resources. There is a specific constraint called resource location constraint that lets you define a list of allowed or denied locations. By setting this policy at a high level, like a folder or the entire organization, you can ensure that no one can create resources outside of your approved regions. This is a proactive, preventative, and centrally managed solution. Therefore, the correct thing to do is configure an organizational policy which constrains where resources can be deployed. Question 213. You need to implement a network ingress for a new game that meets the defined business and technical requirements. Mount Kirk Games wants each regional game instance to be located in multiple Google Cloud regions. What should you do? A. Configure a global load balancer connected to a managed instance group running Compute Engine instances. B. Configure Kubernetes with a global load balancer and Google Kubernetes Engine. C. Configure a global load balancer with Google Kubernetes Engine. D. Configure ingress for Anthos with a global load balancer and Google Kubernetes Engine. Okay, this question from the Mount Kirk Games case study is about setting up networking for a global, multi-region application running on Google Kubernetes Engine. The key challenge is to have a single entry point that can intelligently route users to the GKE cluster in the region closest to them. With that in mind, let's look at our options. Let's start with option A. This is incorrect because the modern recommended platform for this kind of scalable microservices-based game is Google Kubernetes Engine, not standalone Compute Engine instances. Next, let's look at option B, which suggests using Kubernetes. This is also incorrect. While Kubernetes was the original tool for this purpose, it is now considered legacy and has been replaced by a more modern, integrated solution. Option C is close, but it's missing a critical component. A standard GKE ingress object is only aware of services within its own single cluster. It doesn't know how to route traffic to other clusters in different regions. You need a special controller to manage this. This brings us to option D, which is the correct and recommended solution. The modern way to handle traffic across multiple GKE clusters in different regions is called ingress for Anthos, which used to be called multi-cluster ingress. This is a special controller that works with the global load balancer to send traffic to the correct GKE cluster based on your configuration. This is the purpose-built feature for creating a single, global frontend for a multi-region GKE application. Therefore, the correct thing to do is D. Configure ingress for Anthos with a global load balancer and Google Kubernetes Engine. Question 214. Your development teams release new versions of games running on Google Kubernetes Engine, GKE, daily. You want to create service-level indicators, SLIs, to evaluate the quality of the new versions from the user's perspective. What should you do? A. Create CPU utilization and request latency as service-level indicators. B. Create GKE CPU utilization and memory utilization as service-level indicators. C. Create request latency and error rate as service-level indicators. D. Create server uptime and error rate as service-level indicators. Okay, this is a question about site reliability engineering or SRE principles. The goal is to choose good service-level indicators or SLIs for a user-facing application. The most important part of the question is that the SLIs must be from the user's perspective. A good SLI measures what your user actually experiences. You should avoid using internal system metrics, like CPU or memory usage, because a user doesn't care about those. They only care if the application is fast and if it works. With that in mind, let's look at our options. Let's look at option A. It includes CPU utilization. This is an internal metric, not something a user experiences directly, so it's not a good SLI. Option B is also incorrect because both CPU and memory utilization are internal system metrics. They are important for your team to watch, but they are not user-facing SLIs. Next, let's look at option D. It includes server uptime. This is also an internal metric. In a modern, resilient system, a single server can fail without the user ever noticing. What matters to the user is whether their own request succeeds, not whether a specific server is online. This brings us to option C, which is the correct answer. This option lists two classic, user-centric SLIs. Request latency directly measures how fast the application feels to the user. Error rate directly measures how often the application fails for the user. Together, these two metrics give you a clear and accurate picture of the quality of service your users are actually experiencing. Therefore, the correct SLIs to create are C, request latency and error rate. Question 215. Mount Kirk Games wants you to secure the connectivity from the new gaming application platform to Google Cloud. You want to streamline the process and follow Google recommended practices. What should you do? A. Configure workload identity and service accounts to be used by the application platform. B. Use Kubernetes secrets which are obfuscated by default. Configure these secrets to be used by the application platform. C. Configure Kubernetes secrets to store the secret, enable application layer secrets encryption, and use Cloud Key Management Service, Cloud KMS, to manage the encryption keys. Configure these secrets to be used by the application platform. D. Configure HashiCorp Vault on Compute Engine, and use customer-managed encryption keys and Cloud Key Management Service, Cloud KMS, to manage the encryption keys. Configure these secrets to be used by the application platform. Okay, this question from the Mount Kirk Games case study is about securing how your application, running on Google Kubernetes Engine, authenticates to other Google Cloud services. The key here is to find the most streamlined and Google recommended practice, which means we should look for a native managed solution. With that in mind, let's look at our options. Let's start with option B, which suggests using standard Kubernetes secrets. This is incorrect because, by default, Kubernetes secrets are only base 64 encoded, which is not a secure encryption method. It's just a way to hide the text. Option C is a much more secure way to use Kubernetes secrets by enabling application layer encryption with Cloud KMS. While this is a great practice for storing secrets within Kubernetes, the best practice for authenticating to Google Cloud APIs is to avoid needing to store GCP credential files in Kubernetes at all. Option D suggests using a third-party tool, HashiCorp Vault. While Vault is an excellent tool, setting up and managing a separate Vault cluster is not the most streamlined approach and isn't the native Google recommended practice the question is looking for. This brings us to option A, which is the correct and Google recommended solution. The modern way to handle this is by using a feature called Workload Identity. Workload Identity allows you to securely link your application's identity inside Kubernetes, which is a Kubernetes service account, directly to a Google Cloud service account. This means your application pods can automatically get the permissions they need to talk to Google Cloud APIs without you ever having to create, download, or manage any sensitive key files. It's the most secure and streamlined approach. Therefore, the correct thing to do is A. Configure workload identity and service accounts to be used by the application platform. Question 216. Your development team has created a mobile game app. You want to test the new mobile app on Android and iOS devices with a variety of configurations. You need to ensure that testing is efficient and cost-effective. What should you do? A. Upload your mobile app to the Firebase Test Lab and test the mobile app on Android and iOS devices. B. Create Android and iOS VMs on Google Cloud, install the mobile app on the VMs, and test the mobile app. C. Create Android and iOS containers on Google Kubernetes Engine, GKE, install the mobile app on the containers, and test the mobile app. D. Upload your mobile app with different configurations to Firebase hosting and test each configuration. Okay, this is a question about testing a mobile application. The key requirements are that we need to test on a wide variety of both Android and iOS devices, and we need to do it in a way that is both efficient and cost-effective. With that in mind, let's look at our options. Let's start with the options that are technically not feasible, which are B and C. Google Cloud does not offer standard Android or iOS virtual machines or containers that you can just create and use for testing. So these options are not possible. Next, let's look at option D, which suggests using Firebase hosting. This is incorrect because Firebase hosting is a service for deploying and hosting web applications. It is not a tool for testing native mobile apps. This brings us to option A, which is the correct and Google recommended solution. Firebase Test Lab is a specific service designed for this exact purpose. It's a cloud-based app testing infrastructure that gives you access to a wide range of real and virtual Android and iOS devices. You can upload your app and run automated tests across many different device configurations, screen sizes, and OS versions simultaneously. This is highly efficient and cost-effective because you don't have to buy and maintain your own physical device lab. Therefore, the correct thing to do is upload your mobile app to the Firebase Test Lab and test the mobile app on Android and iOS devices. Question 217. Your company has decided to build a backup replica of their on-premises user authentication PostgreSQL database on Google Cloud Platform. The database is 4 terabytes, and large updates are frequent. Replication requires private address space communication. Which networking approach should you use? Google Cloud Dedicated Interconnect. B. Google Cloud VPN connected to the data center network. C. A NAT and TLS translation gateway installed on-premises. D. A Google Compute Engine instance with a VPN server installed connected to the data center network. Okay, this is a hybrid cloud networking question. The key requirements are that we need to replicate a large, 4 terabyte database that has frequent updates, and the connection must be private. This combination of large data volume and frequent updates means we need a connection with very high, consistent bandwidth and low latency. A standard connection over the public internet is unlikely to be sufficient. With that in mind, let's look at our options. Let's look at the options that rely on the public internet, which are B and D. While Cloud VPN provides a secure tunnel, its performance is limited by the public internet, which is not ideal for this demanding workload. Building your own VPN server on a compute engine instance has the same limitations and adds extra management overhead. Option C suggests a custom NAT and TLS gateway. This is not a standard Google Cloud solution and would be complex to implement and maintain, without solving the underlying performance requirements. This brings us to option A, which is the correct and Google-recommended solution for this scenario. Google Cloud Dedicated Interconnect provides a direct, private, physical connection between your data center and Google's network. It bypasses the public internet entirely. This guarantees the high bandwidth and low latency required to reliably replicate a large, active database. It also operates over a private address space, meeting all the requirements of the question. Therefore, the networking approach you should use is a Google Cloud Dedicated Interconnect. Question 218. Auditors visit your teams every 12 months and ask to review all the Google Cloud Identity and Access Management, Cloud IAM, policy changes in the previous 12 months. You want to streamline and expedite the analysis and audit process. What should you do? Create custom Google Stackdriver alerts and send them to the auditor. B. Enable logging export to Google BigQuery and use ACLs and views to scope the data shared with the auditor. C. Use Cloud Functions to transfer log entries to Google Cloud SQL and use ACLs and views to limit an auditor's view. D. Enable Google Cloud Storage, GCS, log export to audit logs into a GCS bucket and delegate access to the bucket. Okay, this is a question about auditing and log management in Google Cloud. The goal is to create a process that is both efficient for analyzing a year's worth of IAM policy changes and secure for sharing that information with auditors. With that in mind, let's look at our options. Let's start with option A, which suggests using Stackdriver alerts. This is incorrect because alerts are for notifying you about events as they happen in real time. They are not a tool for storing and performing historical analysis on a large volume of logs. Next, let's look at option C. This suggests using Cloud Functions to move logs to Cloud SQL. This is not the best approach. Cloud SQL is a transactional database, not a data warehouse, and it's not optimized for the kind of large-scale log analysis required for a year-long audit. BigQuery is the superior tool for this. Option D proposes exporting the logs to a cloud storage bucket. While this is a good way to archive logs for long-term storage, it's not efficient for analysis. Trying to search and analyze raw log files in a bucket is much slower and more difficult than running SQL queries in a dedicated data analytics service. This brings us to option B, which is the correct and Google-recommended solution. This is a two-part strategy. First, you enable logging export to Google BigQuery. This automatically sends your IAM audit logs to BigQuery, which is designed to handle and query massive amounts of data very quickly. This makes the analysis fast and easy. Second, you use ACLs and views to scope the data shared with the auditor. This is the security component. You can create a BigQuery view that only shows the exact logs the auditors need to see, and then grant them read-only access just to that view. This is the most streamlined, secure, and efficient way to handle the audit process. Therefore, the best thing to do is enable logging export to Google BigQuery and use ACLs and views to scope the data shared with the auditor. Question 219. You are designing a large distributed application with 30 microservices. Each of your distributed microservices needs to connect to a database backend. You want to store the credentials securely. Where should you store the credentials? In the source code. B. In an environment variable. C. In a secret management system. D. In a config file that has restricted access through ACLs. Okay, this is a fundamental security question for any application, especially a large, distributed one with many microservices. The core task is to find the most secure and manageable way to handle sensitive credentials. With that in mind, let's look at our options. Let's start with option A, storing credentials in the source code. This is a major security anti-pattern and should never be done. Hard-coding secrets makes them easily accessible to anyone who can read the code, and they can be accidentally committed to source control repositories. Next, option B suggests using environment variables. This is slightly better than hard-coding, but it's still not considered a secure best practice. Environment variables can be leaked through application logs, monitoring tools, or if another process on the same machine is compromised. Option D, using a config file with restricted access, is an improvement but still falls short. While restricting access with ACLs helps, the credentials are still stored in a file on the file system which could be compromised. Managing updates and rotation for 30 services this way would also be very difficult. This brings us to option C, which is the correct and recommended solution. A dedicated secret management system, like Google Cloud Secret Manager, is purpose-built for this task. It stores credentials in an encrypted, highly available vault. It provides fine-grained access control using IAM, so you can define exactly which microservice can access which secret. The services then fetch the credentials securely at runtime via an API, meaning the secrets are never stored in the code, config files, or environment variables. Therefore, the most secure and manageable place to store the credentials is C. In a secret management system. Question 220. A lead engineer wrote a custom tool that deploys virtual machines in the legacy data center. He wants to migrate the custom tool to the new cloud environment. You want to advocate for the adoption of Google Cloud Deployment Manager. What are two business risks of migrating to Cloud Deployment Manager? Choose two. A. Cloud Deployment Manager uses Python. B. Cloud Deployment Manager APIs could be deprecated in the future. C. Cloud Deployment Manager is unfamiliar to the company's engineers. D. Cloud Deployment Manager requires a Google API service account to run. E. Cloud Deployment Manager can be used to permanently delete cloud resources. F. Cloud Deployment Manager only supports automation of Google Cloud resources. Okay, this question asks us to think about the potential business risks of adopting a new standard tool, Cloud Deployment Manager, to replace a custom in-house tool. Business risks are different from technical features. They relate to things like productivity, cost, and strategic limitations. With that in mind, let's look at our options. First, let's look at the options that describe technical characteristics rather than business risks. Options A and D, stating that Deployment Manager uses Python and requires a service account, are simply implementation details of how the service works, not inherent business risks. Option E, that the tool can delete resources, is a necessary function of any infrastructure management tool. This is an operational risk that is managed with proper permissions. And option B, that APIs could be deprecated, is a generic risk that applies to any software or service, not a specific risk related to this adoption decision. This brings us to the two correct answers. Option C states that Cloud Deployment Manager is unfamiliar to the company's engineers. This is a real business risk. A new, unfamiliar tool means there will be a learning curve for the team, which can lead to a temporary decrease in productivity and a higher potential for errors during the transition. It also implies a cost for training. The other correct answer is option F, that Cloud Deployment Manager only supports automation of Google Cloud resources. This is a strategic business risk. The company's existing custom tool might manage resources outside of Google Cloud. By adopting a tool that is locked to a single vendor, they may be creating a new technology silo and limiting their flexibility if they have a hybrid or multi-cloud strategy in the future. Therefore, the two main business risks are C and F. Question 221. A development manager is building a new application. He asks you to review his requirements and identify what cloud technologies he can use to meet them. The application must be based on open-source technology for cloud portability, dynamically scale compute capacity based on demand, support continuous software delivery, run multiple segregated copies of the same application stack, deploy application bundles using dynamic templates, route network traffic to specific services based on URL. Which combination of technologies will meet all of his requirements? A. Google Kubernetes Engine, Jenkins, and Helm. B. Google Kubernetes Engine and Cloud Load Balancing. C. Google Kubernetes Engine and Cloud Deployment Manager. D. Google Kubernetes Engine, Jenkins, and Cloud Load Balancing. Okay, this is an architectural question that asks us to assemble a complete technology stack to meet a list of modern cloud-native requirements. We need a solution that covers container orchestration, continuous delivery, and application packaging. Let's first break down the requirements. The need for open-source technology, dynamic scaling, segregated copies, and URL-based routing all point directly to using Kubernetes, which is provided as a managed service by Google Kubernetes Engine, or GKE. The need for continuous delivery points to a CI/CD tool like Jenkins, and the need to deploy using dynamic templates points to a package manager for Kubernetes, with the most common one being Helm. Now let's look at the options. Options B, C, and D are all incomplete. Option B is missing a CI/CD tool and a templating tool. Option C is missing a CI/CD tool. And option D is missing a templating tool like Helm. They don't provide all the capabilities required by the question. This brings us to option A, which is the correct answer. This combination of technologies covers all the requirements. Google Kubernetes Engine provides the scalable open-source platform. Jenkins provides the continuous delivery pipeline. And Helm provides the templating and packaging needed for dynamic application deployments. Together, they form a complete modern application delivery platform. Therefore, the combination of technologies that will meet all of his requirements is a Google Kubernetes Engine, Jenkins, and Helm. Question 222. You have created several preemptible Linux virtual machine instances using Google Compute Engine. You want to properly shut down your application before the virtual machines are preempted. What should you do? Create a shutdown script named k99.shutdown in the /etc/rc.6.d/ directory. B. Create a shutdown script registered as a Zinit service in Linux and configure a Stackdriver endpoint check to call the service. C. Create a shutdown script and use it as the value for a new metadata entry with the key shutdown script in the Cloud Platform console when you create the new virtual machine instance. D. Create a shutdown script registered as a Zinit service in Linux, and use the Cloud Compute Instances add metadata command to specify the service URL as the value for a new metadata entry with the key shutdown script URL. Okay, this question is about managing the lifecycle of preemptible VMs on Google Cloud. The core of the problem is knowing the specific built-in mechanism that Google provides to allow for a graceful shutdown before a VM is taken away. With that in mind, let's look at our options. Let's start with option A. While using a script in the /etc/rc.6.d/ directory is a standard way to handle shutdowns in Linux, it's not the specific method that Google Cloud uses to trigger a script during a preemption event. There's a more direct, cloud-native way to do this. Options B and D are also incorrect because they suggest using a complex and unnecessary setup with a Zenit service. This is not how Google Cloud handles this process. Additionally, option D uses the wrong metadata key. The correct key is shutdown script, not shutdown script URL. This brings us to option C, which is the correct and recommended solution. Google Compute Engine provides a special metadata key called shutdown script. Here's how it works. You write a script that performs the graceful shutdown of your application. Then, you provide the content of this script as the value for the shutdown script metadata entry on your virtual machine. When Google Cloud is about to preempt the instance, it gives a 30-second warning, and during this time, it automatically executes the script you provided. This gives your application a chance to save its state and shut down cleanly. Therefore, the correct way to properly shut down your application is C. Create a shutdown script and use it as the value for a new metadata entry with the key shutdown script in the Cloud Platform console when you create the new virtual machine instance. Question 223. Your organization has a 3-tier web application deployed in the same network on Google Cloud Platform. Each tier, web, API, and database scales independently of the others. Network traffic should flow through the web to the API tier and then on to the database tier. Traffic should not flow between the web and the database tier. How should you configure the network? Add each tier to a different subnetwork. B. Set up software-based firewalls on individual VMs. C. Add tags to each tier and set up routes to allow the desired traffic flow. D. Add tags to each tier and set up firewall rules to allow the desired traffic flow. Okay. This is a very common network security question for multi-tiered applications on Google Cloud. The main goal is to control the flow of traffic between the different layers of our application, making sure they can only talk to each other in a specific secure way, even when the application is auto-scaling. With that in mind, let's look at our options. Let's start with option A, adding each tier to a different subnetwork. While this is a good way to organize your resources, it doesn't solve the security problem by itself. By default, traffic is allowed between all subnets within the same VPC network. You would still need to add firewall rules to actually restrict the traffic. Option B suggests setting up software-based firewalls on each individual VM. This is incorrect because it's a very manual and difficult to manage approach, especially in an environment that scales automatically. The cloud-native way is to use the centralized VPC firewall service provided by Google Cloud. Next, option C mentions using tags and routes. This is incorrect because it confuses the purpose of routes and firewall rules. Routes are used to direct traffic to its destination, like a traffic cop directing cars down a specific street. Firewall rules act as a security guard, deciding whether that traffic is allowed to enter or not. To block traffic, we need firewall rules, not routes. This brings us to option D, which is the correct and recommended solution. Here's how it works. First, you add a unique network tag to all the VMs in each tier, for example, web tier, API tier, and DB tier. Then, you create specific VPC firewall rules that use these tags. You would create one rule to allow traffic from sources with the web tier tag to destinations with the API tier tag. You'd create another rule to allow traffic from the API tier tag to the DB tier tag. Because the firewall implicitly denies any traffic that isn't explicitly allowed, this setup automatically blocks the forbidden traffic from the web tier directly to the database tier. This works perfectly with auto-scaling because new VMs inherit the tags from their instance templates. Therefore, the best way to configure the network is D. Add tags to each tier and set up firewall rules to allow the desired traffic flow. Question 224. Your development team has installed a new Linux kernel module on the batch servers in Google Compute Engine, GCE virtual machines, VMs, to speed up the nightly batch process. 2 days after the installation, 50% of the batch servers failed the nightly batch run. You want to collect details on the failure to pass back to the development team. Which 3 actions should you take? Choose 3. Use Stackdriver logging to search for the module log entries. B. Read the debug GCE activity log using the API or Cloud Console. C. Use Cloud or Cloud Console to connect to the serial console and observe the logs. D. Identify whether a live migration event of the failed server occurred, using the activity log. E. Adjust the Google Stackdriver timeline to match the failure time and observe the batch server metrics. F. Export a debug VM into an image and run the image on a local server where kernel log messages will be displayed on the native screen. Okay, this is a troubleshooting question that requires us to find the best ways to diagnose a problem at the operating system level on a GCE virtual machine. The key clue is that the failure started after a new Linux kernel module was installed. We need to choose 3 actions. Let's start by evaluating the correct options. Option A, using cloud logging to search for module log entries, is a correct first step. Cloud logging collects the system logs from your VMs, and it's very likely that the new kernel module or the kernel itself wrote error messages to these logs when the failure occurred. Option C, connecting to the serial console, is another correct and very powerful troubleshooting technique. The serial console allows you to see low-level system and kernel messages, which is especially useful if the VM is having trouble booting or is unresponsive over the network. Any kernel panic or critical error messages would likely appear here. Option E is also a correct action. By adjusting the timeline in cloud monitoring to the time of the failure, you can observe the VM's performance metrics. A sudden spike in CPU, a drop in available memory, or strange disk activity could give you valuable clues about how the kernel module was misbehaving and causing the system to fail. Now let's look at the incorrect options. Option B, reading the GCE activity log, is wrong because the activity log only tracks administrative actions on the VM, like starting or stopping it. It doesn't contain any logs from inside the operating system. Option D, checking for a live migration event, is generally a less likely cause. While it's a piece of information you might check, it's not one of the primary, direct ways you would investigate a specific kernel module failure. Finally, option F, exporting the VM and running it locally, is incorrect because it's an extremely slow and inefficient way to debug a problem. The cloud-native tools like cloud logging and the serial console are designed for exactly this kind of remote troubleshooting. Therefore, the 3 best actions to take to collect details on the failure are A, C, and E. Question 225. Your company wants to try out the cloud with low risk. They want to archive approximately 100 terabytes of their log data to the cloud and test the analytics features available to them there, while also retaining that data as a long-term disaster recovery backup. Which 2 steps should you take? Choose 2. Load logs into Google BigQuery. B. Load logs into Google Cloud SQL. C. Import logs into Google Stackdriver. D. Insert logs into Google Cloud Bigtable. E. Upload log files into Google Cloud Storage. Okay, this is a question about a very common big data architecture problem. We need a solution that can handle 2 different goals. First, cheap, long-term storage for a massive amount of data, and second, a powerful way to run analytics on that data. With that in mind, let's look at our options. Let's start by looking at the options that are not a good fit for this scale of data. Option B, Cloud SQL, is a relational database that isn't designed to handle 100 terabytes of data for analytics. Option C, Cloud Logging, is a tool for viewing recent logs, not for long-term archival of such a large dataset. And Option D, Cloud Bigtable, is a high-performance NoSQL database, but it's optimized for real-time applications, not for the kind of analytical SQL queries required here. This brings us to the 2 correct answers, which represent a standard and powerful pattern in Google Cloud. Let's look at Option E, uploading the log files into Google Cloud Storage. This is a correct step because cloud storage is the ideal place for low-cost, long-term archival. It's highly durable and can store virtually unlimited amounts of data, which perfectly fulfills the long-term disaster recovery backup requirement. The other correct step is Option A, loading the logs into Google BigQuery. This directly addresses the requirement to test the analytics features. BigQuery is Google Cloud's serverless data warehouse, designed to run very fast SQL queries on massive datasets. By loading the data here, the teams can easily perform their analysis. Therefore, the 2 steps you should take are A and E. Question 226. You created a pipeline that can deploy your source code changes to your infrastructure in instance groups for self-healing. One of the changes negatively affects your key performance indicator. You are not sure how to fix it. An investigation could take up to a week. What should you do? A. Log in to a server and iterate on the fix locally. Point 1. B. Revert the source code change and rerun the deployment pipeline. Point 2. C. Log into the servers with the bad code change and swap in the previous code. Point 3. D. Change the instance group template to the previous one and delete all instan for CES. Okay, this is a question about incident recovery and DevOps best practices. A bad code change has made it to production, and the fix will take a long time. The top priority in this situation is to restore the service to a stable state as quickly and safely as possible. With that in mind, let's look at our options. Let's start with options A and C, which both suggest logging into a server to make a change locally. This is a major anti-pattern and should be avoided. Manually changing things on production servers leads to an inconsistent and unmanageable environment, and it bypasses all the safety checks of your deployment pipeline. Next, let's look at option D. While changing the instance group template back to a previous version is a valid idea, the action of deleting all instances is incorrect and would cause a major outage. A properly configured instance group would perform a rolling update to the new template, gracefully replacing instances without a complete service interruption. This brings us to option B, which is the correct and most professional way to handle this situation. The process is simple and safe. First, you revert the problematic change in your source code repository, like using git revert. This creates a new commit that undoes the bad code. Second, you simply rerun your existing deployment pipeline. The automated pipeline will then build and deploy this known good version of the code, safely returning your application to a stable state. The long investigation into the bug can then happen in a development environment without impacting users. Therefore, the best course of action is B. Revert the source code change and rerun the deployment pipeline. Question 227. Your organization wants to control IAM policies for different departments independently, but centrally. Which approach should you take? Multiple organizations with multiple folders. B. Multiple organizations, one for each department. C. A single organization with folder 4S for each department. D. A single organization with multiple projects, each with a central owner. Okay, this is a foundational question about how to structure your resources in Google Cloud for effective governance. The key is to find a structure that allows you to manage policies for different departments both independently and centrally. With that in mind, let's look at our options. Let's start with options A and B, which both suggest using multiple organizations. This is incorrect because it goes against the requirement for central management. The organization is the top-level root for your entire company. Creating multiple organizations would make central governance incredibly difficult. Next, let's look at option D, which suggests using a single organization but managing everything at the project level. While using a single organization is correct, this approach isn't scalable. If a department has dozens of projects, you would have to apply the same permissions to every single project individually. This is inefficient and can lead to mistakes. This brings us to option C, which is the correct and recommended approach. The Google Cloud Resource Hierarchy is designed for this exact scenario. You use a single organization for your entire company, which provides that central point of management. Within the organization, you create folders for each department. You can then apply specific IAM policies directly to a department's folder, and all the projects inside that folder will automatically inherit those policies. This allows each department to have its own set of permissions managed independently, while the overall structure is still controlled centrally. Therefore, the best approach is C, a single organization with folders for each department. Question 228. As part of implementing their disaster recovery plan, your company is trying to replicate their production MySQL database from their private data center to their GCP project using a Google Cloud VPN connection. They are experiencing latency issues and a small amount of packet loss that is disrupting the replication. What should you do? A. Configure their replication to use UDP. B. Configure a Google Cloud dedicated interconnect. C. Restore their database daily using Google Cloud SQL. D. Add additional VPN connections and load balance them. E. Send the replicated transaction to Google Cloud pub/sub. Okay, this is a hybrid cloud networking question, focused on a troubleshooting scenario. The core problem is that a cloud VPN connection, which runs over the public internet, is proving to be unreliable for a critical database replication task due to latency and packet loss. With that in mind, let's look at our options. Let's start with option A, configuring the replication to use UDP. This is incorrect and would make the problem worse. Database replication requires a reliable protocol like TCP to ensure all data arrives correctly. Switching to the unreliable UDP protocol would lead to even more data loss. Option C suggests restoring the database daily. This is not a replication solution. It's a backup strategy. It doesn't provide the continuous synchronization needed for a disaster recovery replica. Option D, adding and load balancing more VPN connections, also doesn't solve the fundamental problem. While it might increase the total available bandwidth, each individual connection still travels over the unpredictable public internet, meaning they are all still susceptible to the same latency and packet loss issues. Option E suggests using Cloud pub/sub. This is incorrect because pub/sub is an application messaging service, not a database replication tool or a network connectivity solution. It doesn't address the unstable network connection. This brings us to option B, which is the correct answer. The issues of high latency and packet loss are characteristic of using the public internet. To solve this, you need a dedicated private connection. Google Cloud Dedicated Interconnect provides a direct physical link between your data center and Google's network, completely bypassing the public internet. This provides the high bandwidth, low latency, and reliability needed for a production database replication workload. Therefore, the best way to resolve the latency and packet loss issues is B. Configure a Google Cloud Dedicated Interconnect. Question 229. Your customer support tool logs all email and chat conversations to Cloud Bigtable for retention and analysis. What is the recommended approach for sanitizing this data of personally identifiable information or payment card information before initial storage? Hash all data using SHA-256. B. Encrypt all data using elliptic curve cryptography. C. De-identify the data with the Cloud Data Loss Prevention API. D. Use regular expressions to find and redact phone numbers, email addresses, and credit card numbers. Okay, this is a data security and compliance question about the best way to handle sensitive information found in logs. You've noted that B is the correct answer, but it's worth taking a closer look at the specific requirement, as the Google recommended best practice for this scenario is actually a different option. The goal is to sanitize the data, which means to remove or mask just the sensitive parts, allowing the rest of the conversation to be analyzed safely. With that in mind, let's evaluate the options based on that goal. Let's look at option B first, which suggests encrypting all data. Encryption is a great tool for confidentiality, meaning it makes the entire log unreadable without a key. However, it doesn't sanitize or de-identify the data. To analyze the chat logs, an analyst would have to decrypt them, which would re-expose all the sensitive information. This doesn't quite meet the goal of safely analyzing the non-sensitive parts of the conversation. Now let's consider the other options. Option A, hashing all data, would make the logs completely unreadable and useless for any meaningful analysis. Option D, using regular expressions, is a manual approach that is very difficult to maintain and is likely to miss some types of sensitive information. This brings us to option C, which is the Google recommended solution for this problem. The Cloud Data Loss Prevention API, or DLP, is a service that is specifically designed to find and sanitize sensitive data within large blocks of text. It can automatically detect things like credit card numbers and phone numbers and then de-identify them through methods like redaction or tokenization. This leaves you with a clean, sanitized version of the logs that your team can safely analyze without being exposed to sensitive personal or payment information. Therefore, the most accurate and recommended approach that directly solves the problem of sanitizing data for analysis is C, To identify the data with the Cloud Data Loss Prevention API. Question 230. You are building a continuous deployment pipeline for a project stored in a Git source repository and want to ensure that code changes can be verified before deploying to production. What should you do? Use Spinnaker to deploy builds to production using the red/black deployment strategy so that changes can easily be rolled back. B. Use Spinnaker to deploy builds to production and run tests on production deployments. C. Use Jenkins to build the staging branches and the master branch. Build and deploy changes to production for 10% of users before doing a complete rollout. D. Use Jenkins to monitor tags in the repository. Deploy staging tags to a staging environment for testing. After testing, tag the repository for production and deploy that to the production environment. Okay, this is a question about designing a safe and reliable CI/CD, or continuous integration and continuous deployment pipeline. The most important requirement in the question is that changes must be verified before being deployed to production. With that in mind, let's look at our options. Let's start with option A. While using a tool like Spinnaker with a red/black deployment strategy is a great way to make production deployments safer and easier to roll back, this option completely misses the required verification step before the code gets to production. Option B is also incorrect because it suggests running tests on production deployments. This is a very risky practice. The goal of a good pipeline is to catch bugs before they reach production and impact real users, not to test for them live. Next, option C. This option describes a canary release, which is an advanced deployment strategy. However, it doesn't explicitly mention the crucial step of testing and verifying the changes in a dedicated staging environment first, which was the core requirement of the question. This brings us to option D, which describes a complete, safe, and standard CI/CD workflow. First, it uses Jenkins to monitor Git tags, which is a best practice for triggering deployments of specific versions. Second, it deploys a version with a staging tag to a separate staging environment specifically for testing. This is the critical verification step. Finally, only after the changes have been successfully verified in staging, the version is given a production tag and deployed to the live environment. This is a controlled, safe, and reliable process. Therefore, the best approach is D. Use Jenkins to monitor tags in the repository. Deploy staging tags to a staging environment for testing. After testing, tag the repository for production and deploy that to the production environment. Thanks for watching. If you found this video interesting and helpful, please like, share, and subscribe to our channel. See you in the next video. Happy learning!